Here in this part of uh, concept of power electronics, today we'll try to study about the IGBT. As we have discussed
Oh,
earlier, IGBT is what? IGBT, it is an insulated gate. It's an insulated gate bipolar transistor, right? It's an insulated
yeah.
gate bipolar transistor. So now here, has its on resistance can be modulated, thus the conductivity increases. What does it means? Here in the IGBT, we have a provision of on-state resistance. That means that we can modify this on-state resistance so that we can increase the conductivity of that particular IGBT. So that is
Okay.
that provision is there over here for the IGBT. So as its on-state resistance can be modulated, thus conductivity increases, and it is also known as a COMFET. COMFET means the conductivity modulated FET. So it is another other name for the IGBT. You can also make it clear that IGBT is also called as an COMFET. COMFET. What does COMFET means? Here the COMFET means COMFET is equal to, it is a conductivity modulated FET, field effect transistor. This could be one
Oh,
of your any like short answers questions, or if they ask, we can use this one. So
okay.
IGBT is also called as a COMFET, which is a conductivity modulated FET. Then
Okay.
now here, if you talk about the IGBT, let us see some advantages of this one. It combines the advantages of BJT and MOSFET. Here BJT means bipolar junction transistor, MOSFET means metal oxide semiconductor field effect transistor. So
Oh,
IGBT, which is called as an insulated gate bipolar transistor, itself it tells that IGBT in the abbreviation of this IGBT itself, there is a bipolar transistor, means again it's an insulated gate. The gate is a kind of terminal which is always present with the MOSFETs, in fact with the technology of the MOSFETs. Whereas a bipolar transistors will not have the gate kind of terminal. It will have the only the terminals such as like emitter, base, and collector. But here it's a
yeah.
gate terminal is written insulated gate bipolar transistor. It means it is a combination of, here itself from the name itself we can understand that it's a combination of MOSFET and bipolar transistor. That's a BJT. So let us see the
Okay.
advantages now here. Advantages. First one, it's having low on state voltage drop. The voltage drop will be very less. Then the second one, state, if voltage drop is less, then definitely the power loss also will be less. Why? Because we have studied one formula, P equal to VI, means
Yeah.
the power is directly proportional with the voltage. Okay, fine. And again, we have studied many other formula like P equal to I square R and all those things. So once if the
Yeah.
voltage drop is less, then the power loss also will be less. And the other one, it has got the higher swinging speed than the BJT. We are talking about the higher swinging. So now, what does it mean? We can talk about the swinging part of the BJT. We are talking about the sinusoidal waveform. We are talking about the sinusoidal waveform. The sinusoidal waveform of this one is very good. And again here, the isolation of this particular BJT is very high because of the SiO2. Okay, it has got very
Yeah.
high isolation part. That is, we can write it as by, that is mainly because of the gate which has been designed with the help of the SiO2. We will having a gate. Beneath that one, there will be one insulation. That insulation is called as an SiO2. So these are the advantages. First one is it has got low voltage drop, then low power loss. Then the higher fourth one is higher swing of the speed than the BJT. Here the swinging nature of this speed of this what is it, IGBT is much greater than the BJT, and also it is having the greater isolation part because of the SiO2. SiO2 is nothing else but it's a silicon dioxide which acts as an insulator or the dielectric. Now let us see the construction part. If you see the construction part, before going to the construction part, let us see the symbol over here. In the symbol, we know that for the BJT, we'll be having a base, emitter, and collector. Actually, for the BJT, if this is a BJT, it has to be base over here. But here, it is an insulated gate bipolar transistor. For the insulated gate bipolar transistor, the terminals are gate, collector, and emitter. This is
Yeah.
collector. This emitter and this part is a gate terminal. So you can see the difference over here. For BJT, you will not have this vertical line. Instead, you will be having one line directly drawn from here, from this particular bigger vertical line. Okay, so that is the difference between the BJT and the IGBT. Now you see the construction part. This is how it looks like. You're having an extra layer over here, P plus region, then again N plus buffer region is there, and this N plus buffer region and this part, which is having an NPN transistor and also PNP transistor and NPN transistor. In between that, you are having an epitaxy, N type of epitaxy, and this both will act as N plus buffer, and this region will act as a drift layer. A drift layer is nothing else but it's a layer where the charge carriers can drift from one place to another place. It's all about how the charge movement is happening over here. Then again, beneath the N minus epitaxy, there's a N plus region, and this is a N minus region, and this both are the two active regions, N plus and N minus. What are this N plus, P minus are nothing else, but all this are nothing else, but this is the regions where the concentration of that particular charge is been done. We form this kind of regions with the help of a diffusion process. We make the particular substance to be heated at a higher temperature. Whenever it is heated at very higher temperature, at that particular instant, they try to diffuse a N type of impurities over here in order to form N plus regions. In the similar way, here if I want this P plus region to be formed, here whenever this region has been heated at higher temperature, after getting a sufficient amount of heating and sufficient amount of processed, then they diffuse the P type of impurities over here. That's how the N plus and P plus regions have been formed. Oh, I hope you understand. So now here, this is how we call, and this part you can see, this part is called as a gate region. Gate region, mostly this gate region will be will be designed with the help of the silicons, with the help of the silicon, and this part will act as a body region. Body region is nothing else but we know that for the MOSFET, we have got MOSFET is a 4 kind of terminals. Okay, MOSFET is a 4 terminal. So that what actually happens here, if it is a 4 kind of terminal, we'll be having in the MOSFET, one is a source, drain, other one is a gate, and the fourth one will be the body. The body or substrate, we call it. In the similar way, for the IGBT also, you have got a body region, that's this one, this part. I hope it's clear. What is that we call it? Collector terminal. So IGBT is a kind of device which is a combination of both what is that MOSFET and also a BJT. You can see, these are 3 terminals. This is a collector terminal, this emitter, and this are the gate terminals. So since a gate is being insulated into a BJT, instead of using the base terminal, the gate has been used. So we call it as an insulated gate bipolar transistor. This was the construction of this one. Now let us see the equivalent circuit. Equivalent circuit. What is meant by equivalent circuit? In the equivalent circuit, we'll try to draw a diagram such a way that you will be having a BJT symbol, and also apart from that one, I mean it's not the BJT, I mean the IGBT symbols with along with the PNP and whatever the circuits are there in the construction, and also the resistive parts. Resistive parts. You can see, there is a PNP and NPN over here. The entire structure is what? It's an IGBT. So all these things we will be drawing over here in the equivalent circuit. It's a small signal equivalent circuit. That's how they draw the small signal and the large signal circuits. So see, first one we are having this one where we have a structure where we gate terminal is there, and with the body and all this construction has been given. Then apart from that one, there is a resistor which is a modulating resistor. Why do we need a modulating resistor? Why? Because we have discussed in the earlier of this class that IGBT is a kind of circuit where you can modulate the resistance in order to increase the conductivity. So that's why the modulating has been used. And apart from that, NPN and PNP transistors are there. As you can see, the construction of this one. In the construction, There's an NPN and also PNP transistors. Okay, NPN and PNP transistors are there, and that NPN and PNP transistors. Apart from that one, here the what is that? The base of this NPN is connected to the emitter of this PNP, and these two combined terminals are been connected to a resistor, which is an internal resistance between the base and the emitter. The resistance between this emitter and the base is called as an resistance of base and emitter that is connected over here. So this is how we make the equivalent circuit. So see now, N plus buffer layer and the wide epitaxy layers reduce the gain of the NPN terminal. Thus, the NPN transistor can be eliminated. So here in this one, what's actually happening is that in this NPN transistors, if you see the epitaxy layers, this epitaxy layer and also the N plus regions, N plus region is above the epitaxy layer. This N plus region and epitaxy layers will reduce the gain of this NPN transistor. If the gain is reduced, then definitely we do not require that kind of circuits. Why? Because gain is a kind of parameter which increases the efficiency of a particular transistor. If the gain itself is reduced, then definitely we can say that what actually happens, the efficiency has been reduced. If the efficiency is reduced, we do not require that kind of particular transistor. So here, because of this NPN buffer and also epitaxy layer, the gain of NPN will be reduced. So if the gain is reduced, efficiency also will be reduced. So that's why we do not require the NPN transistors, and we ultimately say that here, since the N plus buffer layer and the wide epitaxy layer reduces the gain of NPN terminal, therefore the NPN transistor can be eliminated. So we can eliminate the NPN transistor. Once the NPN transistor is eliminated, this equivalent circuit is redrawn as this one. You will not be having this particular terminal. Whatever the terminal you can see here in the NPN side, this NPN terminal will not be present. Only you'll be having this particular MOS structure structure, and again our modulating resistor PNP, and also its RBE, that's a resistance between the base and emitter, is present. This the construction of IGBT is identical to that of the MOSFET, except for the P plus substrate. Why the P plus substrate? Because in the MOSFET we have studied while studying the concepts of MOSFET, especially when you try to design a P MOSFET or N MOSFET, the substrate will be of P type. If I'm trying to design a N type MOSFET, substrate will be of P type, and the source and drain will be of N type. Okay, that is one type. If I'm trying to design a P MOSFET, substrate will be of N MOSFET. Substrate will be of N type, and again the source and drain will be of P type. So because of this one, you'll be having only one substrate. Either it will be P or N. But here in the IGBT, you're going to have a P substrate directly above that N plus region. Sorry, N plus buffer region. This P plus region will not be present in the in the MOSFET. So that's why it is written here that the IGBT construction and the fabrication will differ only with respect to the P plus substrate, and everything will, apart from this one, everything will be identical. And this, what is this P plus region? This P plus extra layer at the collector is called as an injection layer. This, if you see the circuit diagram of an IGBT, this P plus is directly connected to the collector terminal. This P plus is directly connected to the collector terminal, and why we are using, since it is directly beneath this collector terminal, and it is called as an injection layer. What does it injection layer means? This injection layer indicates that because it injects the holes into the N plus region. Since it's a P type, it will be full of charge carriers called as holes. So it will be injecting the holes into the N region. Therefore, it is called as an injection layer. Therefore, it is called as an injection layer. So that's why we call the P plus region is called as an injection layer. Why it is called as an injection layer? The main reason is that this extra P plus region at the collector terminal will inject the holes into the N region. That's why it is called as an injection layer. the performance of IGBT is closer to that of the BJT than MOSFET. So therefore, we can say that if you talk about the performance level of the BJT is closer to MOSFET. Why? Because mostly in the MOSFET, see, as per the construction also, if you see the symbol of IGBT has got the two BJT terminals like collector and emitter, whereas it has got insulated gate terminal. So this is as per the symbol also, it looks like it's very closer structure, similar to the BJT. And even though they have, after doing many research works, and they have come to a conclusion that the performance of an IGBT is similar to BJT than compared to MOSFET. And this is mainly because of the P plus substrate. We have used a P plus substrate over here, that you can see the construction over here. In the construction part, the P plus substrate is also been seen. P plus substrate is also seen over here. This, because of this P plus substrate, see, it is written over here, it's a body region. Body, the other name for the body is called as a substrate region. So it's a P plus substrate region. Because of this P plus substrate region, most of the time, the performance of your IGBT will act or will be similar to what we call as a MOSFET. It will be more will be similar to the BJT than compared to the MOSFET. The main reason is that it is because of this P plus substrate. Now let us look into the working condition of this IGBT. So let us see the working condition. We have seen that IGBT has got one gate terminal, one collector terminal in the top, and one emitter terminal in the bottom. Those are the three terminals. Now let us see the working condition of IGBT. When gate is made more positive with respect to the emitter, you're supplying a more positive voltage, means the gate voltage is greater in positive terminal than compared to the emitter, means your gate terminal is having a if let me give as an example, if a emitter terminal voltage is +2 and gate terminal is +5, it is called a more positive. Or else if I say that if emitter terminal is something around minus, something like minus 0.1 or 0.2 or -1, and gate terminal is +6 or +7, it is called more positive. You're applying a voltage in positive at the gate terminal which is greater than the emitter terminal. So therefore it is written here that when the gate is made more positive with respect to emitter, then what will happen here? N carriers are drawn into the P channel near the gate region. Because it's more positive means what? It is full of positive charges, holes. Since it is made, gate terminal is made of full positive, means it's full of holes. And we know that the opposite charges will attract. So whenever the gate is made more positive, then definitely the N type of carriers are drawn into the P channel near the gate. So N type of carrier, what is that? Charge carriers will come very close to the gate terminal. That exclusively they are drawn into the P channel which is present near the gate terminal. We have seen just now in the construction, it is clearly mentioned in the P channel only the gate terminals are there. So therefore, whenever the gate terminal is made more positive, N type of charge carriers will get attracted towards the gate terminal and they come closer to the gate terminal. That means they are drawn into the P channel. This results in a forward bias of the bias. So what will happen whenever this happens? Whenever the N type of charge carriers come closer to the gate terminal, what will happen? This is called as a forward bias of the base of an NPN transistor. And once if the forward bias of the BJT, if BJT enters into forward bias, what happens? The transistor will be in the turn on nature. The BJT, always keep in mind, the BJT, whenever it's in the forward bias, it will be turned on. Whenever it's in the reverse bias, it will be turned off. So now in the equivalent circuit, we have seen that we are having NPN transistor and PNP transistor. Whenever this gate is made more positive, N type of charge carriers will come very close to the P channel, which is nearer the gate terminal. Whenever this kind of phenomenon takes place, then what happens? The BJT will become as that's the NPN BJT will become as a forward bias. Whenever that NPN is forward bias, it will be turned on. Now, when the positive voltage VCE, what is this VCE? This VCE is a voltage which is present between the collector and emitter. When the positive voltage VCE is applied to the collector with respect to emitter, the P collector region, the collector region is P type. Why? Because I have told you there in the diagram, it is mentioned that beneath that collector only we are having the what is that P region? It is called as an injection region. Why it is called as a P injection region? Why? Because it will inject the holes into the particular IGBT. So therefore, it's called as a injection region. So now your collector is a P region. Whenever I apply a positive voltage VCE between the collector and emitter, that means it is applied to collector with respect to emitter. The P collector region injects hole into N plus drift region. Beneath that one, there is a N plus region is there. So therefore, it will inject the holes into N plus drift region. Thus, N region is flooded. Means N region will be flooded with the electrons from P body region and holes from the P plus collector region. So therefore, your N plus now your N plus region, N region will be having electrons from the P body region and also holes from the P plus collector region. So thus the current is due to both the charge carriers. Therefore, the current will be due to electrons and also holes. So this is what is happening. This is how it looks like. You can see now diagrammatic part has been mentioned over here. This is a gate terminal. Okay, beneath that one, what I told, beneath the gate will be always an SiO2. I told it's a silicon region. The voltage between the gate and the emitter will be VGE, VGE, and now it is an N plus region and P plus region, N plus P plus. You can see now there are like NPN transistor and also PNP transistors embodied within this particular IGBT. Here, whenever the electrons are moving, if electrons are moving here, what I told, the N region, this part, I'm talking about the N region, which is over here. It's not the N plus, I'm talking about only the N region. This N region, this part, what will happen? It will be flooded with the electrons from the P body region. P body means what? It's a P substrate from the P body region and holes from the P plus region. So that's how the N region will be flooded with both the electrons and also with the holes from the P plus collector region. In this way, the current will be flowing. Current means what? Whenever the charge carriers are moving across any of the particular terminals, that flow of charge carriers itself we call as a current. So since here in this N region, electrons are moving from P body region into the N region, and also holes are moving from P plus collector region into N region. So into the N region, electrons are coming from P body. Electrons are moving means what? Current is produced due to electrons from P body to N region. In the similar way, holes are coming from P plus region to the N region. So that's how the electrons and current is mainly because of both the charge carriers. Is it clear? I hope it's clear to you.
Yeah, sir.
So see now the types of IGBT. First type is called as punch through IGBT. Now here N plus layer or the buffer layer is present in this punch plus IGBT. Thus has asymmetrical blocking. Asymmetrical blocking will be done. What is meant by asymmetrical blocking? It is very much clear in the BJT concepts. You can see there. We will be talking about the forward blocking voltage and reverse blocking voltage there. Thus it has an asymmetrical blocking over there. And the swinging time of this is reduced by use of heavy doped N plus buffer region. So this is about your punch through IGBT. So if I go to the non-punch through IGBT, in the non-punch, excuse me. If I go through non-IGBT, in the non-punch IGBT, you will not be having a N plus buffer layer. N plus buffer layer is absent, and carrier lifetime is kept more than that of a PT structure, which causes the conductivity. Here in this one, the carrier lifetime will be more. Carrier lifetime means we are talking about the charge carriers. There will be more. There will be in the conductivity more than compared to the previous one, punch through. structure. PT means punch through structure. So now because of that one, which causes the conductivity modulation of the drift region. Since the carrier lifetime is more, means what? The carriers will be moving for longer time. Because of that one, the conductivity also will be, there will be change in the conductivity of the drift region, and thus it reduces the on state of the voltage drop. Because of this one, since it's having the, it causes the conductivity modulation. Because of that one, there will be less voltage drop. Now transfer characteristics. So this is a transfer characteristics between the current and the voltage. The voltage between the gate and emitter, and this is a collector current. Here, initially you'll not be having any kind of current. Why? Because the particular transistor has to turn on. The transistor hardly it is turning on over here at 5. Uh, so now from there it will be increasing. Okay. So this is called as a cutoff region, and whenever it starts increasing, that's where we call the transistor is coming into on state. Once it comes into on state, then depending upon this voltage, the current also will be increased. So that's about the transfer characteristics, and now the output characteristics. This is how the output characteristics looks like. Depending upon CNO, here you cannot find any kind of region in the beneath part. Below VG is 6 volts, because the transfer characteristics is starting somewhere around 5 volts. Beneath that, hardly you can see this output characteristics. Once the voltage is 6 volts, the input voltage VG is 6 volts, then you can see the the output characteristics of a what is that? This particular IGBT. It is also VI characteristics, but it is an output at the output part of the IGBT. For different voltages, we can see whenever the voltage input voltage, that is a VG is 6 volts. This is the transfer characteristics, where it's current is hardly it's less than 1. Again, for VG is 7 volts, the current is almost 1, or slightly higher than 1. If you talk about this input voltage, VG is 9 volts. Here the current is almost 4 amperes. 4 amperes. And when it comes to the input voltage, VG is 10 volt, the current is somewhere in between the 6 and 5 amperes. So this graph tells about this transfer characteristics and the output characteristics for any structure is most important one. We are supposed to remember that both the transfer characteristics and output characteristics. Now let us see the advantages. The advantages of IGBT. It combines the advantages of BJT and MOSFET. So it is having, it's like high in this one. So input characteristics like a MOSFET. Then again, the voltage control device, like it's a voltage control device. You can see in the previous stage, depending upon the VGE, only the output is varying. So therefore, it's a voltage control device like a MOSFET, simple gate driven, and it is having a lower switching loss. The switching loss will be less, and it's a gate driven one. Why? Because it's having one of the terminal is gate. Whenever you apply the gate voltage, whenever the gate becomes more positive, then only the operation is starting over there. Electrons have been driven towards a P substrate near the gate terminal. So here it's a gate driven terminal. It's a gate driven structure and having a lower switching loss. Now low on the on state conduction power loss, like BJT, it's having low on state conduction power loss. The power loss is low. Why is the power loss low? Because the voltage drop is very less. If the voltage drop is very less, that happens mostly in the BJT. So that's why it is having, just like the BJT, there is a low power loss. If power loss is low, that means the voltage drop is also low. It's having the higher current driving capability like the BJT, and higher swinging capability. Okay, higher swinging speed than BJT. The current capability is also high, and also the swinging speed is also much higher than the BJT. These are the advantages, and let us see the disadvantages over here now. The disadvantages are, it's having an asymmetric blocking. Asymmetric blocking is one of the disadvantage. You can just refer the BJT in order to understand what is this asymmetric blocking. And the next one is switching frequency is less than compared to the MOSFET. So these are the advantages and disadvantages working procedure of an IGBT. I hope you understood this IGBT concept. Now let us see the application part. The applications of IGBT. Applications of IGBT, it is seen in the AC and DC motor controls, general purpose inverters, UPS, and also is used in the welding equipments and robotics and induction. So these are the applications of IGBT.